tells us that the evolution of the galaxies and their central black holes are actually tightly correlated, which tells us something very important about evolution of galaxies. Gamma ray bursts. So gamma ray bursts were discovered a long time ago, but then the Gamma Ray Observatory was discovering them about once a day, and it was very embarrassing that for a few years they collected a few thousands of gamma ray bursts, and we did not know, because the Gamma Ray Observatory was not able to tell us very accurately, you know, where the burst is. The error boxes were quite large. We couldn't identify them in any other wavelengths, and as a result, we were unable to tell whether these gamma ray bursts are all the way across the universe or in the halo of our own galaxy or where. So basically, we didn't know if they were in our backyard or you know, halfway across the universe. But then, by a combination of an X-ray satellite, in that particular case was an Italian satellite named Beppo Sachs, and optical observatories on the ground, we were finally able to locate these things. And in particular, what Hubble did in this field is, for the first time, it showed us images of the host galaxies of these gamma ray bursts. This way, we discovered that gamma ray bursts are actually at cosmological distances, namely they are really scattered all across the universe. They happen in galaxies of all types. You see sometimes here, you see it happens right in the arm of this spiral galaxy. Of course, gamma ray bursts are easier to find if they have green circles around them, but we drew them after the fact. The thing to notice here that they don't occur especially at centers of galaxies, because you might have thought that maybe they have some clear activity of galaxies, but they absolutely don't. I mean, in this case, look, it's on an arm. Many times it's completely off from any center that you can tell. And we now know that at least a part of these gamma ray bursts, these ones in particular, which are called long duration gamma ray bursts, these are gamma ray bursts that last longer than 2 seconds or thereabouts. They can last even up to minutes. Are associated with collapses of very massive stars. So they are the same type of things that produce some supernova explosions, but they produce these very powerful gamma ray bursts. There is a second class of gamma ray bursts that are called short duration. These are the ones that are shorter than 2 seconds, and they are thought to be the result of merging two neutron stars that are in a binary system. Those are primarily observed by the satellite called SWIFT. Stellar populations in nearby galaxies. So this is the Andromeda galaxy, one of our nearest neighbors in the local group, one that is about the size of the Milky Way. So the observations that were done here were in the halo of Andromeda, so very far from the center. So look, this is what the field looks like, and this is what the Hubble image looks like. There are about 100,000 stars in this image. Look here, you can see lots of galaxies in the background through the halo of Andromeda. And also look at this globular cluster of stars here. This is a collection of stars of about 100,000 to 1 million stars that you see in Andromeda. But the interesting thing about this is by looking at local group galaxies, Hubble is able to resolve all the stars in these galaxies and to tell, as a result of this, what are the ages of these stellar populations and so on. So for example, the halo of our own Milky Way galaxy is kind of uniformly old. And you know, it's about maybe 12 billion or there are 10 to 12 billion years. In Andromeda, there was a surprise here, because in the halo it was found that there is one population that is as old as the halo of the Milky Way, but there is a second population that is about 4 or 5 billion years younger than that population. So the question is, why is that? But you remember that I told you that galaxies evolved by mergers and coalescing. And what we think happened was that some 4 or so billion years ago, Andromeda suffered one major collision with one of its satellite galaxies, and that collision actually kicked stars from the disk into the halo, and this is why you see this population that is considerably younger. So by looking at these nearby galaxies, we can tell how stellar populations evolve, and thereby, also understand things about how very distant galaxies or galaxies evolved a long time ago. Now here I'm showing you a simulation of two galaxies colliding, and every now and then this is stopped and shows a Hubble image of two galaxies interacting, and you will see how you can get very close matches between some of the results of this simulation and the results of some images that we have actually taken with Hubble. Here is another one. Now this is the same simulation that just continues in time, and every now and then you see we freeze it, and then we show you a Hubble image of a pair of galaxies that were actually observed, and you see how closely they match. Of course, you never know at which angle you are going to see this, so we have to rotate sometimes the simulation to give you the match. And we released about a year ago 59 such colliding galaxies. The birth of stars and planets. So we look at a variety of stars, young stars that are being born. Theoretically, we always thought that when a cloud of gas collapses, because of angular momentum, it forms a disk, and there are jets from that. But we now actually have seen this. Here is that disk, the illuminated upper and lower surfaces, and the two jets that come out of the star. In other cases, we've measured outflows. This is just a couple of years. You can see the outflow as it is advancing. This is the Orion Nebula, one of the nearest star-forming regions to us. I'll show you a close-up of some of these places. And I draw your attention to things that look like this. This is a dark disk of dust, and there is the star in the middle. Here is another one. You can see the star peeking through this dust disk. Here you can also see that something is formed here. What these are protoplanetary disks, and the Orion Nebula is full of them. These are the dust disks from which planets actually form. What happens is that then the dust coalesces, it forms rocks, the rocks coalesce, they form things, eventually planetesimals, things like Earth. Then things like Earth, well, sometimes stay like Earth, but if there is gas, they accrete gas on top, they become things like Jupiter. Here you can see a few close-up images of some of these protoplanetary disks. Here is the dust disk, the very narrow dust disk. Sometimes you can see the microjets that emerge from these forming stars. Here is another region of star that is forming stars. Here you can see the jet coming straight out of the column of dust and gas. The famous Eagle Nebula. There are bright stars here. They illuminate and sculpt the environment. The radiations erode all the less dense material and leave only the densest columns behind. The columns always point, as a result of this, to those very young, bright stars. The Cone Nebula, and this is the Carina Nebula, another famous star-forming region. Here is the star that is about to explode any minute, or maybe has exploded already, only we haven't seen it yet. Here is the Loch Ness Monster coming there. So all kinds of columns of gas and dust. If you take a closer look at some of the regions here, like that region there, here is a star being born. You can see the two jets and their bow shocks. Here is another star being born, the two jets and a series of bow shocks in both directions. In 1994, a comet collided with Jupiter. we thought this was an absolutely once-in-a-lifetime